In this figure, a circle is inscribed in a square. This means the circle essentially fits inside the square or touches it precisely at these four locations, right? This is the idea of a circle being inscribed in a square. You might also see the word circumscribed. That would be the reverse, where you have a circle, and then inside the circle would be a square. Right? In this case, right, the square touches the circle at these 4 points, right, at the vertices. So in this situation, you might have seen this before, but this is referred to as circumscribed, right, and this is inscribed. So here the circle is inscribed. All right. Well, the square has a side length of 4 units, we're told. So that means that, right, the square on each side, here and every other side, of course, because all sides are the same, are 4 units. They want to know, find the area of the circle and the shaded region. Well, okay, the area of the circle, right? The circle, we do know that the diameter is also 4, right? Because the diameter of the circle stretches right across the square and equals the side length of the square here, right? So I know I'm looking at my image right here and I'm realizing it's not a great image, but the square goes right from here to here. That white border around the square is just part of the image I cropped in. So that means the diameter is 4 and the radius, which is half the diameter, is then 2, right? So r equals 2. So circles, right, are equal to pi times the radius, or, right, pi radius squared. This is the area of a circle. So what does that mean? Well, here if the radius is 2, that means you have pi times 2, which is pi times 4, or more typically written as 4 pi. And with the units, this would be 4 pi units squared, right? So in terms of pi, right, in other words, 4 pi's, or 4 times pi, which is over 12, right, over 12, that is the area of the circle. What is the area of the shaded region? Well, here with the shaded region, you can almost imagine if you have this square, right, this full square, and then you were to cut out the circle, right, so this whole region here, you're to cut it out. What will be left is the shaded region. So to find the shaded region, right, we have the circle area. Oops, let me write this in this way. So the shaded region, that's just going to be what? Well, it's going to be the square area minus the circle area. Okay, well, the square area is just 4 by 4, or 16 square units. So we have 16 square units minus 4 pi square units. Now, if we're leaving things in terms of pi, that's it, we're done. But here, I guess we can estimate pi as well. They don't ask for a degree of accuracy, I don't think, but here, let's say pi is about 3. That's the nearest whole number. Then the shaded region would be what? Essentially 16 minus 4 times 3, or 16 minus 12, which is just 4. So 4 square units, right? So what's interesting about that, of course, if we estimate pi to 3, and you notice the circle is equal to 4 pi units, notice the shaded region is just equal to 4. So you might want to ask, right, does that mean that if the circle is 9 pi units, would the shaded region then be just 9? Well, let's find that out, right? Let's just pretend here, because you want to ask those what-if questions, right? So here, if the radius equals 3, then the area of the circle equals 9 pi. Then what happens? Well, the square is 16 minus, well, here, and this is the fun part, I think, you realize, oh, I can't fit that circle with an area of 9 pi inside a square that is 16 by 16. What would that be? Well, this time the circle has a radius of 3, right? So the diameter will now have to be 6. So we have this new square, which is 6 by 6, or 36. So now, if we simplify this, we would get 36 minus 9 pi, or 36 minus 9 times 3, or 27. And that's 36 minus 27, which is 9. So there it happens again. If you take the area of the full square minus the circle and estimate pi to 3, you just get the coefficient of the area. right? This number here is the coefficient. So you want to think, well, will this always happen, right?